today we're going to look at some questions that are going to help you guys review for benchmark number 6. I will have the video paused every once in a while so that you have a few minutes to look through the question on your own and try to answer it on your own, and then I'll go through the solution together with you. The first question says, if the area bounded by the curves xy equals 9 and x plus y equals 10 is revolved around the x-axis, the volume of the generated solid is equal to, and then it gives us 5 answer choices. So let's talk through the problem just a little bit first, then I'll give you a minute to solve it on your own, and then I will continue to solve the problem together with you. So first of all, it's probably a good idea to get a rough sketch of what this looks like. So for the first function, xy equals 9. If we solve for y, we get that y equals 9 over x, which is a rational function that has been stretched by a factor of 9. So if I draw this, a rational function that's been stretched by a factor of 9 probably looks something like that, as well as like this. For the second function, we have x plus y equals 10, so therefore y equals negative x plus 10, which is a line that intersects up here at 10, as well as over here at 10, and goes down like this. So it says, if the area bound by the curves of xy equals 9 and x plus y equals 10 is revolved around the x-axis, so our axis of revolution is right here on the x-axis, the volume of the solid generated is equal to yada yada yada. So essentially we're trying to revolve this area right here. I would like to pause the video here, pause it for about, I would say 5 minutes. And then we'll see where we left off. See if you guys can get an answer in the next 5 minutes. Okay, so hopefully you had a chance to look at this on your own. Let's go ahead and draw our circles that would show where it's being revolved. So remember that the center of our circles will always be the axis of revolution. If I go to the closest point in the area, it looks like that. If I do it again, but going to the furthest point in the area, it looks something like this. So looking at my 2 radii, this first one, the outside radius, goes from the top of that red circle down to the actual function, down to the bottom. So the length of this line is top function minus bottom function, so that's going to be the line minus 0. So that's negative x plus 10 minus 0, which is just negative x plus 10. So the big radius is equal to negative x plus 10. The little radius is right in here, so I'll draw it right there. So this little teeny tiny one that I drew right here, that I know that I didn't draw it perfectly, I should draw it right here, but you wouldn't be able to see it. So the top function minus the bottom function, so it's 9 over x minus 0. So the little radius is equal to 9 over x. Now, as far as where these are going to be equal to each other, where they intersect to find the limits of integration, you can go ahead and set them equal to each other and solve for what x is going to be. But if you look at all of your answer choices, I'm pretty sure the limits of integration are going to be 1 and 9. So I'm going to try and use my knowledge of multiple choice questions to try and help me out a little bit. So let's just make sure by checking. If I plug in 1 here, I get negative 1 plus 10, which is 9. And if I plug in 1 here, I get 9 over 1, which is also 9. So yeah, that is definitely the first point of intersection. So this point right here in, let's do purple, is x equals 1. All right, so I know that this point is x equals 1. Let's verify that this one over here is x equals 9. So if I plug 9 into this, I get negative 9 plus 10, which is 1. If I plug in 9 here, I get 9 divided by 9, which is 1. So yes, this one is in fact x equals 9. So you could have done that by hand by setting these equations equal to each other and solving, but might as well use our multiple choice answers to help us out with that. So let's keep going. Remember that these create these cylindrical shapes, and so we're going to do the, to find the area of each of these circles, it's pi r squared. So remember that for the integral, we have pi times the integral from 1 to 9 of the outside radius squared, so that's negative x plus 10 quantity squared, minus the inside radius squared, so that's 9 over x quantity squared. And that's dx. Sorry, it kind of ran into the other part a little bit. So negative x plus 10 quantity squared minus 9 over x quantity squared, I believe that would be answer choice B. So B is the correct answer for that one. All right, let's move on to the next one. If you needed that last problem a little bit longer to copy down what we wrote, maybe rewind the video a little bit and pause it. For this next part, it says the base of a solid is the region enclosed by y equals e to the x. So let's start sketching this. Oops, my bad. Y equals e to the x looks like this. The x-axis and the y-axis and the line x equals ln of 3. All right, x equals ln of 3 is probably somewhere right here. And we're going to draw a vertical line right there. All right, so the area that we're trying to look at is the area enclosed by the exponential function, this line, the x-axis, and the y-axis. So it's that area right there. It says cross-sections perpendicular to the x-axis are squares. So again, when you're looking at it from the top, from a bird's eye view, it is a square, but it kind of looks like that. If you kind of tilted it over to the side, you would see that it was an actual square like that if you looked at it from the side, but we'll look at it from the top. So remember that areas of squares, oh, sorry, I don't want to give away too much. Why don't I have you guys pause the video again? So pause the video here, take about 3 to 4 minutes, possibly 5, depending on if you need more, and see if you guys can find an answer for this one, and then we'll come back together again. So pause the video for about 5 minutes. Okay, so as far as finding the integral for all of these, we're looking for cross-sections that are squares. So remember that the area of a square is side squared. So if I can figure out the length of this red line, then I can just square it to figure out the area of one square. So remember, we're integrating from the furthest point to the left all the way to the furthest point to the right. So we're going to go from 0 to ln of 3. So volume equals the integral from 0 to ln of 3 of the length of this line here is the top function minus the bottom function. So that would be e to the x minus 0, which is just e to the x. And because that's the expression that represents the length of this red line, that's one side of the square. To find the area of that square that we're looking at, we just square it, dx. So the integral from 0 to ln of 3 of e to the x squared dx is the same thing as answer choice C. Notice that D and E had some pi's in them. All right, we don't need pi in it if we're doing cross sections. That's only if we're revolving things. So that's kind of a trick to make sure that you know that we're working with cross sections and not revolutions. Notice that this one has ln of 3 squared. Some people maybe tried to plug in ln of 3 into the function, but I don't care about the y value. I care about the x value, which is ln of 3. And then this one up here at the top forgot to square e to the x, so don't fall for that one. So if you need to pause the video to write this down, go ahead. If not, let's move on to our last problem. So before we actually do the problem, I just want to talk about total distance versus position one more time. We've talked about this before, but I think some people still have an issue with finding total distance. So if you're given velocity, there's two things we can do given velocity. Well, there's multiple things, but the things we're going to talk about here are you can either find total distance or you can find the position. So I want to really quickly talk about the difference between both of those when you're given a velocity function. I've given you guys the example before where let's say that you're driving on the 15 freeway here from Ontario. If you drive, 15 miles north, or if you're down in San Diego and you drive 15 miles north, or if you're up in Las Vegas and you drive 15 miles north, the total distance doesn't matter where you begin. It does not matter what the initial condition is. All that matters is how far you have traveled, all right? And notice that, if I kind of expand on this story a little bit, let's say that I start driving 15 miles north from here. Oh no, I forgot my wallet at home. I better drive back and go get it, and then keep going forward up to go 15 miles north. Notice that total distance would include the amount that I drove at the beginning, going back home, and the amount that I drove at the end. So that's the absolute value one. Versus position if I forgot my wallet at home and I drove, 5 minutes, then came back and got my wallet and then kept driving, notice that it does not include, so positive and negatives cancel each other out. So position would just say, like if I accidentally had to backtrack a little bit, it would erase that. So the positives and negatives would erase each other, and I would just say, where's the displacement? So where did I start versus where did I end? And notice that for that one, it does matter where you begin. So if I'm in San Diego and I drive for 15 miles versus here and I drive for 15 miles versus Las Vegas and I drive for 15 miles, even though my total distance might be the same, my position will depend on where I started. So let's look at what it looks like. For total distance, I'll just abbreviate that TD. It's going to be equal to the integral from a to b, whatever your a to b is, of the absolute value of the velocity function. And that will give me total distance. For position, however, I have to take into account my initial condition. So let's just say that my initial condition, I'll just make up something, is 0, 1. All right. So if I look at my initial condition, I start at 1. I start at whatever position that I start at, and I accumulate area from 0 all the way up to whatever I want to end at. So let's just say B. And notice that this is not the absolute value because I don't want it to take, sorry, that should be a T. I don't want it to take into account if I had to go backtrack and retrace my steps. I just want it to take into account the displacement, which would not be the absolute value. So notice that I included that initial condition. So if I start at time equals 0 and I'm already at a position of 1, I've accounted for that, and I will accumulate how much area or what the displacement is between where I start and where I finish. And again, back to total distance, I want to account for all my retracing of my steps as well. So let's do a problem that pertains to this. Total distance versus position. It says the velocity of a particle moving along the x-axis is given by the function 2 sine of 2t plus 1. If the particle is at x equals 1 when t equals 0, what is the total distance traveled and the position of the particle at t equals pi over 2? So let me separate our workspace into two areas. So over here we're going to do total distance, and over here we'll do position. So pause the video for a few minutes and see if you guys can set up the integrals and begin to solve the integrals that help us to find the total distance as well as the position for these two functions. So take about 3, 4, 5 minutes, however long you need, to see if, at the very least, to see if you can set up the integrals, and then once you get the integrals, begin to solve them. All right, so for total distance, remember that it's the absolute value function, so it should be the total distance equals the integral from, we start at 0 to pi over 2, of the absolute value of this velocity function. So the absolute value of 2 sine of 2t plus 1 dt. All right, so there's the integral for total distance. For the position, remember that we get to use our initial condition. So this is, it says my initial condition is that x equals 1 when t equals 0. So we are starting at 1. Plus the integral from 0 to pi over 2 of the function without absolute value. So just 2 sine of 2t plus 1 dt. So that's the setup of the integrals. If this was a calculator question, you could just really quickly plug it into your calculator. If it's not a calculator question, however, you have to account for that when you actually take the integrals. So let me see if we can finish solving this together. If you didn't get these integrals correct, all right, make sure to write them down. Pause the video for just a few more minutes, maybe 2 or 3 more minutes for people to try and solve these and see if you can get an answer for them. And then we'll go through together at the very end to do it together. So pause it for about 2 or 3 minutes. Okay, so let's look at position first because I don't want to have to deal with that absolute value just yet. So for position, it's equal to 1 plus the integral of sine of 2t, 2 sine of 2t, I'm sorry, is negative cosine of 2t. And you can check to make sure we did that correctly, because if you take the derivative of negative cosine of 2t, cosine's derivative is negative sine, so those negatives would cancel. The derivative of the 2t would be 2, so that's where that extra 2 comes from, so that way you know you've done it correctly. And the integral of 1 is just t, so plus t. And we're going to do the fundamental theorem of calculus from 0 to pi over 2. So the fundamental theorem of calculus says to do f of b minus f of a. So if I plug in pi over 2 to both of these, and then subtract plugging in 0 to both of these. So let's do pi over 2 first. If I plug pi over 2 in here for t, I get 2 times pi over 2. Well, 2 times pi over 2 is pi. So that's negative cosine of pi plus pi over 2 minus, if I plug in 0, I get negative cosine of 0 plus 0. Well, we can keep going. I get 1 minus, I can probably take away those parentheses from the outside, so minus cosine of pi is equal to negative 1. So that's going to be a negative 1, which is going to turn into a positive 1, plus pi over 2. Cosine of 0 is equal to 1. So here I have negative 1, so that's positive 1. And then minus 0 is just going to go away. So if I finish this problem off, I get 3 plus pi over 2. All right, so that's for position. For total distance, we have to take into account this absolute value. You have to think if this this function is ever going to equal 0 and turn positive versus negative versus whatever in the interval from 0 to pi over 2. So as far as that is concerned, we should probably take a look at the graph of this function. And so if we do that, we get the sine function normally looks like this, where this is all the way over here at 2 pi. Remember that this 2 in here compresses the graph by a factor of 2 horizontally. So instead of it taking 2 pi for it to take its whole period, this b value divides that, so now it's only pi units. So if I erase that 2, now my period would be pi units, which means that right here in the middle, this is pi over 2. And this 2 stretches it by a factor of 2, and this 1 shifts it up 1. So it's going to look something like this. So good news is that from 0 to pi over 2, all of this area is above the x-axis. None of it dips below the x-axis. So the cool thing is that we don't have to worry about the absolute value, because between 0 and pi over 2, our entire area, our entire integral for that red function is above the x-axis, and so the absolute values will have no effect because it's already positive. So that's kind of a plus for us, so we don't have to worry about that. So we can drop those absolute value bars. So now I just have the integral from 0 to pi over 2 of 2 sine of 2t plus 1 dt. Well, like I said, over here we already did that. The only thing is that we didn't need this extra 1 for total distance. So if you go through the same exact steps as we did over here, but instead of adding that extra 1, we just have the integral itself, which is the displacement, we end up getting 2 plus pi over 2. So the answer to this is 2 plus pi over 2. And that would be the total distance traveled. So that's all we're going to do for today. Make sure that you have some good notes, work on that diagnostic, and we will go from there tomorrow as our last day before we take our benchmark.